All right. Here we are again, Thursday morning, ready to roll with some more cool math. All right, let's see what we've got for ourselves today. So we're going to carry on with chapter 5C, which we just barely started the other day. Also, though, what I want to do now, because we're getting pretty far along into chapter 5, if you look at Moodle, you'll see that there are problem sets here. There's actually 3 of them. Now, these are not meant to be collected like regular homework. These are just practice problems. So what I would like to be able to do is have you start working on the first 2, because you're ready for them now. Each one is meant to go with one section of chapter 5 anyway. So why don't you do this over the weekend? Take a look at chapters of problem sets number 1 and 2, and then we'll go over them on Monday. And when we're done with chapter 5C, then we'll go to 5-3. Right? So this is all purely for practice. You don't have to send it to me. You know, these are just all the problems that we've been working on. So this way you can make sure that you really understand what we've been doing. Down the road, we'll have a test sooner or later, probably later, and it will be based on chapters 5 and 6. But for now, what I will just want to do is make sure that we're keeping up with the material by working on these practice problems. In the meantime, we're going to start 5C, but we also have 2 more cool videos today, very cool videos, as a matter of fact, which will help, again, tie together everything we've been doing in a very, very interesting way. I think you'll agree when you see them. But in the meantime, why don't we get back to where we were? So we'd started just barely to look at these properties of the real numbers. And you'll recall there were 6 of them. And the first couple, I think we've already done. Closure, for example, we're just saying here that the sum of any 2 real numbers is also real. Let's see, what else did we cover? Closure. Oh, and this also holds for multiplication. Yes. So in other words, if you add real numbers together, the result will also be real. It's not possible for an imaginary number to result from either adding or multiplying 2 real numbers. All right, we covered that. What else did we do? Yes, oh, associative. Okay, very good, thank you. We did, so yeah, let's jump ahead to the associative property then. Associative basically is telling us under what conditions the parentheses do not affect the results. I mean, that's essentially what this is all about. So for example, here, if we're only adding, we don't actually need these parentheses at all, because if you see here in the first case on the left-hand side, if I put the parentheses around a plus b, over on the right-hand side, I have them around b plus c. These are both the same number. And that's what associative means. Now, normally, parentheses are really being used to override the order of operations. So if you've got mixtures of multiplication and subtraction and exponentiation, and you want to change the order in which the values are being evaluated, that's when you really need parentheses. For something like this, you don't actually need them, because this is not going to affect any results. And that's because all of these operations are the same order of precedence. All addition, all multiplication, you know, it's not going to be, these are not required. So let's look at some examples of this. Like, for example, clearly in parentheses 1 plus 2 plus 3, this tells us to evaluate 1 plus 2 and then add the 3 to it, which gives us 6, of course. Down here, we do it the other way around. We start with the 1, we evaluate 2 plus 3, and that way we have 1 plus 5, but of course that still gives us 6, any way you look at it. Then down here, same type of situation. We combine 3 plus 6 in the parentheses to come up with 9. We then add the 7, and we end up with 16. Whereas down here, we have 3, and then we add the result of adding 6 and 7, which is 3 plus 13. And again, we wind up with 16. So in a case like this, the order of the parentheses is completely irrelevant. And so this is what we call the associative property of addition. Now, we can also make the same claim for multiplication. The order in which I put these parentheses is completely irrelevant. In fact, we don't really need them at all, because they do not affect the results. And again, that's because all of the operations here are at the same level of precedence. So just a couple of quick examples. In parentheses, 2 times 3 times 4 means 6 times 4, or 24. Here we'll have instead 2 times in parentheses 3 times 4, which means 2 times 12, and that finally gives me 24. Now, you notice down here, though, we have negatives involved, and still the results are the same. So, for example, here with in parentheses negative 1 times 4, all times 5 means I have negative 4 times 5, or negative 20. Whereas down here, I've got negative 1 times in parentheses 4 times 5, which is the same thing as saying negative 1 times 20, or at the end, you'll see I still have negative 20. So the associative property is applicable to both addition and multiplication. All right, now the identity property. This is where it gets interesting, and this starts to tie us back to that video we were watching the other day about why you can't divide by 0, by the way. So first of all, we have the so-called identity property, and this is where they tell us formally that if you add 0 to a number, it does not change our result. Okay, in other words, adding 0 to any constant a means we still have a. And for that reason, we often refer to 0 as the identity element for addition. That's what it means, okay? So in other words, 0 is the only number which we can add to another number and yet not change the result. So 0 is a very interesting number. It really shows up in a lot of interesting ways. As we already have seen, it was one of the last numbers to be invented because, it was a very mysterious concept and it wasn't absolutely clear why we needed one. But now, of course, we see that it is one of the more important numbers. All right, now this also applies to multiplication. And this is what they discussed with us in the video, but we'll see in a second. For multiplication, the identity property is simply that if you multiply any number by 1, you still end up with the same number. So therefore, it makes sense that we call 1 the identity element for multiplication. Okay, so we've got 2 identity elements, 0 for addition, 1 for multiplication. All right, so then now what this leads us to is the following very interesting result. Inverses. Okay, so remember, this is based on the identity elements. 0, again, for addition, 1 for multiplication. What we can do now is rearrange these equations to define what's called an inverse. Now, as it turns out, there's an inverse for both addition and for multiplication. When you hear the word inverse, you're usually referring to the multiplication case, but there does exist one for addition as well. How does that work? Okay, so look at what happens here. If you take any a and add negative a to it, you'll wind up with 0, which of course 0 is our identity element. So in other words, what we're essentially saying is that for any a, there's an operation you can perform that gives us the identity element, and that operation is to add negative a or subtract a, which is the same thing. But for that reason, we call negative a the additive inverse of a. Okay, so any a and negative a are additive inverses of each other because their sum gives us back the identity element for addition, 0. And I think, of course, everybody knows that intuitively, but it's good to see this written out more formally. And of course, here what we're trying to do is justify this result. In fact, a lot of what we take for granted in math, it's all based on formal proofs. Everything in math is done based on proofs so that you don't have to inspect each case individually. You can make a claim, for example, that a certain situation is always true, no matter what numbers you're using. And that's how math works. Everything has to be proved. You can't take anything for granted or on faith. It doesn't work that way. It's just, if you want to say something make a claim, you've got to be prepared to prove it. And not only prove it for one case, but for all cases. So that's what's happening here, no matter what A is. If you notice, A is any real number. It doesn't matter which one. It could be 3 or negative 502. It doesn't matter. If we add its negative, we end up with 0. Now, how about multiplication? This is the one you're probably more familiar with. Whatever A is, if you multiply it by 1 over A, you'll wind up with 1, of course. And of course, we know that 1 is the identity element for multiplication. So here we say that 1 over A is the multiplicative inverse of A. So just as a quick, simple example, if A is 3, then its multiplicative inverse would have to be 1/3, because 3 times 1/3 is clearly 1. So these are multiplicative inverses of each other. Now, of course, remember in the video, they're saying how here's the reason why we can't divide by 0, because there is no, this is the one exception, there is no multiplicative inverse for 0. All right, there's none. It doesn't exist. There are no numbers. A times something, let's call it X, never equal 0 unless A itself is 0. All right, so or the other way to look at it is you can't divide this thing, because this would imply that, hold on a second. Let me just rewrite this a little bit. Let me just take a step backwards here. In other words, what this is all about is that the fact that this is true means that 1/3 is the inverse of 3. But with A, if A is 0, it's not the case that A times X, 0 times X equals 1. There is no X that satisfies this equation. This is what the problem is. There isn't one. Here we have no problem. If we start with 3, we multiply it by 1/3, we get 1. If we start with 0, though, there is no real number X whose product with 0 will give us back a 1, which means there's no multiplicative inverse for 0, which implies we can't divide by 0. And that's the end of that. So sorry, no division by 0. It's not allowed. All right, now the distributive property. This is one you're very comfortable and familiar with, even if you don't remember the name of this property, because you do it all the time in math. What does it tell it? Now, this one specifically is the distributive property of multiplication over addition. So you have something like this. And that just means, listen, you've got A times in parentheses B plus C. Now here, if you notice, we're combining multiplication and addition, and you know multiplication takes precedence over addition. What the parentheses are doing is overriding that and saying, listen, you can do the following. You can either add these together and then multiply by A, but if you do, you're just going to wind up with this, AB plus AC. So what you're basically doing is saying multiply the A times the B, and then you add A times C. And this is your final result. So for example, 3 times 4 plus 1 would be 3 times 4 plus 3 times 1, which is 15. Now, if you do this with variables, 3 times x plus y, for example, you're going to wind up with 3x plus 3y. This is where it really is more helpful. Down here with this case, you could just as easily have done this. 3 times 5 is 15. So you don't really need to apply the distributive property here. This is where it really is helpful. when you're applying constants to variables, and you can see this and this are the same thing. Okay, so this one you know by heart. You just haven't, maybe you've forgotten what it was called, but you knew intuitively that this is how it works. And that's because somebody taught it to you very well many, many years ago, and you've not forgotten it. All right, so some quick examples. I did it two ways in both of these cases, just so you can see here. What I've done is I've combined these into 7 to give us 14. But here I actually applied the distributive rule, 2 times 3 plus 2 times 4, and I end up, of course, with 14 in both cases. Now down here, I've done the same thing. I've consolidated these two, which I can certainly do, to come up with negative 30. Or if you multiply these and these, you'll get negative 3 times 4 plus, now here this is a negative, so I can actually just subtract 3 times 6. And of course, I'll wind up with the same result. All right. Now we're done with these properties. We're going to sort of take a step back and review something that you're very familiar with. Two things you're actually very familiar with, but possibly you've started to forget some of the important details. And that would be exponents and scientific notation. Now, you probably were introduced to this in science, whatever science classes you took. Anytime you encountered numbers that were either really huge or really tiny, we often find it convenient to write them in what we call scientific notation, because it helps us avoid writing a lot of zeros. Like, for example, like the speed of light. Now, just to be on the safe side, I'm going to go look it up. I may have forgotten the exact number. Oh my God. That's a lot of miles per second. I wonder how far. Now, remember the concept of light years. Light travels how far in a year? Here it is, 6 trillion miles. That's right. That sounds familiar. So 6 trillion is a big number. It's 6 followed by 12 zeros. That's a lot of zeros. So we'll see a shortcut note method that will make it a little quicker and easier to write this out, because it is an enormous number. So we'll get back to that in a few minutes. First, we're going to review everything we need to know about exponents. So what exactly is an exponent? Well, this is what it actually means. If you multiply a number by itself any number of times, let's say we'll call this n times, then this notation tells me that I have taken a and multiply it by itself n times. So let's say, for example, I take 4 times 4 times 4. This is 4 to the 3rd power. That's what it actually means. Okay, so exponents have a lot of interesting properties. For example, by the way, if you're going to write it out like this, I just want to point out that for this expression, we know that this is an exponent, but you might have forgotten that this number that's being raised to the nth power is called the base. Okay, so you have a base and you have an exponent. Now, you may also have a constant being multiplied out here. For example, we could call it k. And if we do, this k is called a coefficient. It's not always there. If there's no k there, it's just implicitly a 1. But so here we have a base, we have our exponent, and if there's a constant there, we call it a coefficient. Okay, some very high-powered words here, but I think we intuitively already understand what an exponent is. So now here's some quick and simple examples. For example, here we have 2 to the third, or this is also called 2 cubed. Most of the exponents don't have names, but cubed and squared do. And that's just 8. If you want to confirm that in your calculator, you can certainly do so. This calculator has the exponentiation key. Let's see, I think it's x to the y power. This is your iPhone I'm talking about. Yeah, on your iPhone, the key you need for all of these is x to the y power. Except for the 2 special cases, there's already an x squared there and an x cubed. For those 2, you can just use those buttons. For the rest, you need to use this. Like, for example, here, to obtain this in your calculator, you would put 3 x to the y. And because it doesn't know which exponent you want, you have to tell it to use 4. And then you would hit the equal button. And there, wait, I think I screwed it up. Hold on. 3 exponent 4. There it is. Okay, great. But for something like this, you can just write 5 and then hit the x squared key, and it should give it to you directly without needing any more buttons. So I don't know who invented this notation, but they really did the world a service, because this really saves you, as you can see, a lot of writing. All right, but then we get interesting cases. Now these, if you notice, are all positive integers. When we have other exponents, then things get very interesting. Like this one. By definition, raising anything to the 0 power gives us 1. Okay, that's important. Anything raised to the 0 power just gives us 1. All right, how about this one? Ain't raising anything to the 1st power gives us that number. All right, raising it to the 1st power means you don't change it, because you're just, basically it just means you're not even multiplying it, it is that number. All right, negative exponents. Now people can get confused about these. The negative exponent doesn't mean you have a negative number necessarily. It means that you're creating an inverse. This is important, because I've noticed a lot of people over the years are a little bit fuzzy about this one. So just don't put a negative in there. It's just 1 over a to the positive n. Now we're going to look at a couple examples, and I want to make sure you can all implement these on your calculator. All right. So how about these 2? Now, if you're going to use your calculator, you have to also now be able to create negative numbers. So here you would put 3 exponent. Now this is where you have to be careful, because in this calculator, negatives are created by putting that number and this special plus minus sign. So, and then you still need the equals. Now you might notice, if you do this in your calculator, you're getting 0.111111. But based on what we've seen before, this is actually a rational number, and it's equal to 1/9. Now, if you want to prove that to yourself, there's a button in here somewhere on the extreme left-hand side of the calculator. It says 1 over x. If you hit 1 over x, it'll give you back 9. So that just proves that this number up here is 1/9. This is a very handy little button, by the way, if you've not noticed it before. It's way in the far left underneath the second sign, the second button, and this is the inverse. This 1 over x stands for multiplicative multiplicative inverse to distinguish it from the additive inverse, of course. So that flips over and affect a ratio. So if you start with 2/3 and you type that button, it will give you back 3/2, although it will write it as 1.5. It doesn't have the capability of writing out fractions. Some calculators do, but not this one. But you should notice, I mean, 1.5 is 3/2. Now this one, of course, is very similar. It's 5 to the negative 3, which is 1/5 cubed. And that should give you back the decimal equivalent of 1/25, which is about, hold on, 0.0, it's exactly 0.008. So if you want to confirm that, if you hit the 1/x button, it'll give you back 125. And so you say, that tells me that this 008 must be 1/125, and that is exactly correct. Good, excellent. So so far, all the properties we've seen, I think most people remember them. This is the only one that I've seen give people trouble in this group. This concept of a negative exponent. It's an inverse. Just think of it as an inverse. Fractional exponents. We talked about this the other day. So you should remember that the square root of any number is in fact just that number raised to the 1/2 power. These mean the same thing. This is, I don't know who invented this symbol or why, but it is meant to replace this. They both mean the same thing. Just be aware of that. Who knows? Maybe if I do some research, maybe I can find a video that explains the origin of these symbols. It might be very interesting. We take them for granted, but at some point somebody had to invent these symbols, and it had to catch on. In other words, you can invent all the symbols you want, but if people don't use them, it doesn't go anywhere, does it? I guess you could say that inventing new symbols in the Middle Ages was like creating YouTube videos today. You never know when it's going to catch on. All right. How about this one? Now, I think we also discussed this one. Yes, no, isn't it kind of the same thing? If you wanted to be famous in the Middle Ages, one thing you could do is invent a new symbol. And that, not that you have gotten any royalty payments or anything, but you got to claim that, yeah, this is my symbol. Oh, no unpleasant flashbacks. Okay, no, we'll avoid that. Oh, good. Okay, yeah, I don't know when the technology fails and doesn't fail. You can usually expect it to fail. And when it doesn't, you should be pleasantly surprised. That's how you have to look at it. Anyway, so 8 to the 1/3 is the cube root. Now, if you notice here, there's a little 3 here. We did not have that before, although you do sometimes see it. Usually the 2 is left out because it's understood that if there's no number here, it is the square root. Although your calculator does label it that way. If you look at carefully, your square root key on the iPhone does have the 2 listed there. They must have decided that it would be too confusing if they left it out because it's right next to this one. And of course, let's stop and think for a second what it means to be a cube root. The cube root of 64 is 4, which you can prove on your calculator. But that is just simply telling us that 4 cubed is 64. So taking a cube root and cubing a number are basically inverses of each other. So if I were to do something like this, now you can see the connection. This has to give us 4. It's like you're cubing it and taking the cube root. It's no different than doubling a number and then dividing it in half. If you double 2x times 1/2 is just x. It's the same principle. The 2 operations are inverses of each other. Now, this next one, though, is going to get very challenging. Let's look at a case. This is a very odd case. Let's take a look at this one. What happens if the exponent is not 1/3 but 2/3? Well, basically what you're doing is taking the cube root of a squared. And if you get confused, you can remind yourself of this by doing the following. I think you'll agree that 2/3 equals 1/3 times 2. So watch what happens if I write it like that. Oh, actually, no, let me write it the other way around. 2 times 2/3, that'll be easier. And so now I'm going to write it like this. And by doing it this way, you can see that this, sorry, I messed it up again. I'll get it, don't worry. Okay, there we go. So in other words, given that 2/3 is nothing but 2 times 1/3, if we break this up into those two pieces, you can see that now what I'm effectively doing is saying, why don't I take this whole expression and multiply it or raise it to the 1/3 power? And so therefore, this is the logic behind why 2/3 means take the third or cube root of a squared. So if let's do another one. If you had a to the 4/5 power, it means that you're taking the fifth root of a to the 4th. So I think if you write it out like this, it will be more clear what you're supposed to do. That's my opinion. You don't have to do this, but I think by splitting it up into these two pieces, you can see more clearly that this is the same as this. So this way you'll never get confused. Now, what if I throw a monkey wrench in there? What would happen if I had a to the minus? Oh my God. All right, don't panic. First of all, this is nothing but 1 over a to the 3/4. And based on what I showed you a second ago, a to the 3/4 could be thought of as a cubed times 1/4, which is the fourth root of a cubed. So that is what's going to go in the denominator. So with the negatives, remember the negative is just an inverse. Once you get it down here, you've got this fraction. Rewrite the fraction. Try to do it as the whole number times the fraction. And then it should be very clear what this represents. In this case, it's the fourth root of 1, a cubed. And you're done. So if you understand what we just did, this example in particular, then there's no case that could possibly confuse you. And of course, if it has no negative, you don't even have to bother with this first step. Now, if you wanted to do this on your calculator, though, watch what you would do. Let's say I wanted to evaluate. Oh, let's do these. Now you know that this is the square root, but just for the heck of it, why don't we take this and instead of using the square root button, why don't you use the exponentiation key just to get some practice? And if you do, it's a little bit messier, but this is the general approach. And if you do this properly, you will, of course, get a 3. So it's 9, exponentiation key. And then the exponent is the result of taking 1 divided by 2, close in the parentheses, equal, and you should get your 3. If you had 1/9 or 9 to the negative 1, let's say this is 9 to the 1/2. Let's try 9 to the negative 1/2. The difference would be 9 exponent. What you would have to do here is take 1, make it negative, and then you're going to take the division sign, 2 close equals. Now it's going to come back with this. Actually, no, it's not. Sorry. It's going to come back with 3s. But we know that this is just 1/3. All right, let's try that one. 9 exponent, open parentheses, 1 negative divided by 2 close equals. So again, if you understand what we just did, there's no case that you'll not be able to handle. The negative means just you can make the numerator negative. It doesn't really matter in this case. The denominator could be negative too, but either one has to be negative, and then you have your final result. Okay, now x 8 to the 2/3. Again, remember what this is all about. Oh yeah, that's just equal to 8 to the, the cube root of 8 squared, which is the cube root of 64, which if you go to your calculator, you'll see is in fact 4. And then finally, the cube root of 8, you can use the cube root function if you want to, and you should get a 2, or you can raise it to the 1/3 power like we did here. 8 exponentiation key. And you should get a 2. All right, so I think we're getting pretty good at this stuff, aren't we? Yes, we are. All right. It's too bad I can't see your calculators. Yes. Feel pretty good. Feels good, doesn't it? Yeah. You walk around your town knowing that you are the exponentiation king or queen, as the case may be. Now, what about more complicated cases? What if we need to perform algebraic operations on exponents? There are 3 basic categories. Exponentiation royalty, exactly. That's who you are now. Don't make sure everybody knows it. Put up posters of exponents in your room. They'll get the hint. Okay, yeah, there's plenty of room in that room for math posters, I bet. And of course, the old refrigerator has plenty of room on it too, doesn't it? Yes, it does. You can get rid of all those magnets and replace them with with math posters. I'm sure people would appreciate it. That's right. No land or money, but you've got that title, your exponentiation royalties. You know it. All right. But if we need to apply algebraic operations here, then we have all these special rules. Yeah, I noticed that those special symbols, they don't turn into the little faces like they do on, let's say, Microsoft Word. But we get the idea. That sideways things, I don't know how many there are. There doesn't seem to be a dictionary anywhere that says, hey, these symbols turn into faces. I've never seen it on the internet. What is that one? Oh, that's the opposite, isn't it? That means no good. I think so. Oh, I didn't know. See, that's why they need a dictionary for this. But they couldn't call it a dictionary because they're not words. They'd have to come up with some weird name for it. Oh, I see. It's like a humorous demon or something like that. Demon with a sense of humor. All right, but anyway, so we have these 3 rules that we can apply to exponents, and they're pretty straightforward. Mischievous, yes, exactly. Yeah, some of those Norse gods fall into that category. They had the most interesting mythology, I think, of anybody. But anyway, so let's start with the simplest one, the product rule. Now, if you were to take two numbers that have the same base, but different exponent, or they could be the same exponent, it doesn't really matter, but as long as they have the same base, you can just add these together. All right, this is what we call the product rule. So in other words, if you had 2 to the third times 2 to the fourth, you end up with 2 to the 3 plus 4, which is 2 to the seventh. Now, you could confirm that by writing these out separately. For example, this is 8 and this is 16. And if you were to write out 2 to the seventh on your calculator, you'd see that it is in fact 128, which is the product of 8 and 16. But for many applications, it's quicker to just combine the exponents than try to evaluate each term separately. So just remember, when we have a product like this, as long as we have the same base, the exponents can be combined, and that gives us our new result. And of course, let me just show you again why, based on what these numbers actually mean. 2 cubed is this. Whoops. 222 is 2 cubed. And 2 to the fourth is just 2 times itself 4 times. And so you end up with just 2 times itself 7 times. And that's why the rule works. And so that's the logic behind why this rule works. Yeah, it's one thing to say, okay, let's memorize this rule, but it helps a lot if you really understand what's going on. And this way you can say, oh yeah, of course. And then you'll never forget it if you truly understand it. All right, now let's do some examples. And so again, I've done it twice. In the second case, I've used the rule by combining these. 2 to the fifth is 32, but here what I've done is evaluated each one separately, and you can see that it must give me the same result. So in the calculator, if you want to do it this way, if you can type 2 y to the x to the y power 3. Let me just confirm this real fast. 2 I think in this case, you have to hit the equal sign first. Yes, and then you multiply by 2 raised to the second. Let's see what happens then. And then if you hit equals, yeah, okay, that did it, 32. Now that looks like a lot. You can see why you might be tempted to just say, oh, for God's sakes, it's just 2 to the fifth power. And then look how much quicker that is. 2 raised to the fifth equals. And you'll get your same 32. And then down here, based on the same logic, here I can consolidate these exponents to give me 3 to the 6th, which is 729, or I can evaluate them individually and still wind up with 729. All right. Now, of course, if there's a product rule, you can probably imagine that there's also going to be a quotient rule. if we can multiply these together, why not divide them? Oh, there's more. Ooh, look at this. Now, these are somewhat more challenging because we've got negatives in this case and we've got zeros down here. Look at that. So, of course, here, this is actually nothing but 1/2 times 8, which is 4. But if I add them up, I get 2 squared, which is, of course, 4. Down here, now the 0, remember, 4 to the 0 is 1. Anything to the 0 power is just 1. But that makes things simple. This is clearly 16. And now down here, if I add 0 to 2, it just stays at 2. And I end up with 16. Any way you look at it. All right. And if there's fractions involved, I don't think I have any examples of fractions. Let's just throw a quick fraction in there. How about, I don't know, 4 to the 1/2. Ooh. And 4 to the 3/2. Oh my God. I didn't plan to get too tricky here, but this is 4/2. Oh my God. It's just 16. But if you were to evaluate these individually, this one would be 2 and this one would be 8, and you'd still get 16. But you can see this always works. As long as we have the same base, we can always add our exponents. Very well. Now, like I started to say before, if there's a product rule, there must be a quotient rule. And this time, instead of adding the exponents, you're subtracting them. Okay. Now, by the way, I just want to demonstrate that this is really nothing but a special case of the addition rule, because watch this. This is the same thing as a to the m times a to the minus n. And then if you add those together, oh yeah, it's the same, isn't it? So this is just a quicker way of remembering it. But you can see it is really just an application of the product rule. So just remember, when we have a ratio, we subtract. When we multiply, we add. But when we have a ratio, we subtract. And that's the way to go. But this is actually what's going on behind the scenes. Oh, and of course, this time we do have one more thing to worry about. We can't have 0. Okay, so it does say any non-zero real number. A is restricted, in this case at least, from being a 0. Otherwise, you know what happens. Oh, division by 0 in math, the worst thing you can do. All right, so let's look at some quick examples. So here, I've done it 2 different ways. You can evaluate them individually, or here you can see that I've got 5 minus 3, which is just 2 squared, or 4. On your calculator, you can do it either way. If you choose to do it this way, you would need to take 2, raise it to the 5th, equals, and then you would have to divide by 2 to the 3rd. That's a lot of steps. I think you'd agree that just 2 squared might be the way to go. So, but they do mean the same thing. How about if we get negatives involved? We can actually have some interesting results here. Or what if the numerator is smaller than the denominator? All right, let's look at some more cases here. Like, look at this case. Oh, what's going on here? Well, here I've got 9/27, or 1/3. Down here, by applying the rule, I've got 2 minus 3. And of course, you recognize that 3 minus 1 is 1/3 to the first, which is itself just 1/3. All right. So let's see if there's any more good examples here. All right, I think we get it. Oh, here's one. Let me try a tricky one on you. How about this? Ooh, what do we do now? Well, if we apply the rule, just remember, when you subtract a negative number, it becomes positive. So that one is a little tricky. Just be careful with it. If I had this, ooh, it gets even trickier. And that becomes 3 to the 3 plus 2. Minus 3 plus 2, which is 3 to the minus 1. All right. Now, there's one more, which is called, and again, this is really just an extension of the product rule, but that's okay. It makes things a little simpler for us. And it is referred to as the power rule. Now, this is different. Do not confuse this with this case, because what's happening here is that you've got a to the m, and then all this entire expression is raised to the nth power. So in other words, equivalent of, let's say, 3 to the second power, all raised to the third power, versus 3 squared times 3 cubed. They're not the same thing. This is the equivalent of 3 times raised to the 2 times 3 power, 3 to the 6. Over here we have 3 to the 2 plus 3, or 3 to the 5th. It's not the same, is it? No. Now, let me show you why this is happening, because look what I've got here. This is just shorthand for saying 3 squared times itself 3 times. And now by applying the product rule, you can see that I've got 3 to the 6th. So I would say this is one of the more challenging ones, but as long as you're careful with it, you shouldn't have any problems. Very good. All right, so let's take a look at some examples. And we'll see that, you know what, they're not that bad after all, are they? No. Okay. All right, so for example here, now I've done it twice in each case, as I have done all along. Here I've evaluated 2 cubed to become 8, and 8 squared is 64. But here, if you look at this carefully, you'll see it is the product power rule, rather. And so I've got to multiply 3 times 2 to get 2 to the 6th, and I end up with 64. Down here, what I've done is I've evaluated 3 to the 4th first, and then I squared it. But here, I'm actually applying the power rule, which means I'm multiplying these, and I'm getting 3 to the 8th, which is 65/61. All right. Now, that concludes our discussion, our very intensive discussion of exponents. What's coming next is scientific notation. So rather than dive into that, I want now for us to get out our cool videos and be prepared to be amazed when you see these 2 videos. They're designed to be informative and fun, but they're also going to make you think about math in a way you haven't before. All right. So, yes, that's how amazing these videos really are. All right. What I'm going to do, as usual, is I'm going to go to Moodle and open up the links. We're going to start with something called the infinite hotel paradox. Now, paradox is something that it's something that seems to contradict something you think you know. And so this is really about infinity and the ways infinity can surprise us. So let's start with that one. And like I said, you will be prepared to be amazed by this thing. Right? But as usual, I'm going to have to send it to you in the chat room. Here we go. So let's check this thing out. Are you all blown away? We got to learn more about not only infinity, but prime numbers. We know there's an infinite number of them now, and we can see one of the consequences of it. We also know that there's different levels of infinity. Oh my God. You'll never be the same after that, will you? No. All right. Are we all done watching it? All right. So now, luckily, the next one is very different. This is more about how math shows up in the real world. All right. So after a mind bender like this one, we need to calm down a little bit and see all the many different surprising ways in which math shows up in the real world. I think that we could use some of that now. Would you all agree? Yes. Yes, we do. It was no, that was cool. No, whoever, I mean, if any of you are studying graphics or art or anything, I mean, you can tell us. I mean, that was very well designed, wasn't it? Yes, it was cool. It was just fun to watch. And that's what you want from an educational video. It's just you're going to remember that for a long time, aren't you? The Infinite Hotel. Yes, you are. Um, yes, and you're going to have more appreciation of how cool prime numbers are and infinite numbers. So, all right. Anyway, so this next one is more about what's going on in the real world, uh, and you're going to be surprised by some of these. It's called "Interesting Facts About Numbers and Prime Numbers." So you can tell it's going to be good. Here we go. Um, hold on one second. I'll pop that into the chat room and then we can check it out. All right, let's give this one a watch. Okay, you know what? I just realized I didn't send it to the right address. You should have it now. All right, can everyone see it? All right, go ahead and watch it. All right. Is everyone done? Yeah, bees can count. Who knew? Oh, that video was filled with fun facts, wasn't it? Yeah, it was like too much almost to remember everything. You have to go back. But imagine that guy was counting to 1 million. There was actually people in the audience watching him. Can you imagine a more boring activity than watching somebody recite all the numbers from 1 to 1 million? I don't know. That takes a lot of self-discipline. I guess they were hoping that he missed one. I don't know. That was kind of weird. But it took him 89 days of just sitting there counting out loud. I don't know how anybody could have that kind of yeah, that was kind of weird. I guess Carl Sagan, I didn't remember that. He had a series of famous shows on TV, but I do not remember him talking about prime numbers like that. I'd have to double check that. He was a very famous astronomer. He was at Cornell. I mean, he was very, people took him very seriously. I just didn't know that stuff about the aliens. But anyway, so yes, there's all kinds of interesting ideas floating around in that video. And I mean, you can make a ton of videos about all the different ways math shows up in our lives. It's just, the history is that rich. And of course, you do expect numbers to show up everywhere, and they certainly do, in some very surprising ways. But anyway, so what I'd like to do now, we have a little bit of time left. I'd like to at least start our discussion about scientific notation, partially because you've probably already seen this. You've just probably started to forget about it. So it's not a terribly complicated topic, but we probably could use a little review. Okay, so again, as I mentioned before, we're going to use this for cases when we have either extremely large or extremely small numbers. And it's really just a way of writing them out in a more compact way, where it's just more about convenience. That's the only reason we have scientific notation. So yeah, for example, 1,220,000 can be written in scientific notation as 1.22 times a million. And of course, a million is 10 to the sixth power. Now, just in case you start to forget the powers of 10, oh crap, I forgot to turn on the video. There we go. Oh, all right, are we all seeing it now? Sorry about that. I forgot to turn the video back on. Let me quickly step back. We're looking at scientific notation, and so like I was saying before, this is defined to give us a way of expressing either extremely large or extremely small numbers in a way that is much more compact than writing out all those zeros. In other words, these numbers have an enormous number of zeros, and that's why it's more convenient to write them in a slightly different way that means the same thing. So basically what we're doing is we're reducing them all to the product of some number and a power of 10. Okay, so the whole thing is based on powers of 10. All right, so let's do this example again. 1,220,000 can be written as 1.22 times 1 million, and 1 million can be written as 10 to the sixth power. All right, if you're not sure, you can check it out with your calculator. Either that, or you can notice that 1 million, if you look at it carefully, you can see that it does in fact have 6 zeros. So that's why it makes sense that 10 to the sixth is 1 followed by 6 zeros. Okay. So this is where we're going now. Like I started to say, just in case we need a little refresher about powers of 10, I've put together this nice little table for you. So now, of course, 10 to the 0 power is just 1. We saw that earlier, that a to the 0 is just equal to 1, and that includes the 10. Same thing here with 10 to the first. 10 to the first is just 10. Now, here we go. Now we're getting into the interesting ones. 10 squared is 100. 10 cubed is 1,000. 10 to the fourth is 10,000. 10 to the fifth is 100,000. And 10 to the sixth is 1 million. These are large numbers. That's getting to be a lot of zeros. And so it may be more convenient to write these large numbers in the form of scientific notation. And by the way, just for the fun of it, what would you say is the name associated with 10 to the ninth? This is millions. 10 to the ninth is billions. Or 1 followed by 9 zeros. And of course, then what comes next? Oh, what did I do? 10 to the 12th is, what's the name for that? Anyone know?
1 trillion.
1 trillion, exactly. Not a gazillion. Gazillion is a slang word. There's no such thing as a gazillion. We say that when we mean something that's enormously large, like, well, anyway, a trillion. Now, you may have encountered this number in your daily routine. What do I mean by that? Well, take a look at your hard drive on your laptop. If your hard drive has 1 terabyte of storage, this translates into 1 trillion, what are called bytes. That's an actual word, by the way, byte with a Y. Of storage. Each byte holds a single number, letter, or character. So if you have a 1 terabyte hard drive, there's 1 trillion bytes of storage on it. Okay, which is a lot. Even at this point in time, that's a pretty significantly large hard drive. TB stands for terabyte because the prefix tera means trillion. All right, so now you know. A trillion. And now you know what the word byte means. So your computer stores information in 1 digit at a time, 1 decimal, 1 letter, whatever. They're all referred to as bytes. All right. And just for the fun of it, what comes next? We ran out of space here. 10 to the 15th, I'll sneak it in down here, is called 1 quadrillion. Now, let me show you a fun application of this. Everybody knows what inflation is, I guess. You've heard it, you know what it means. It means when prices are rising. There have been a handful of cases in history where inflation got really, really, really out of control. For example, Germany after World War I, their inflation rate was probably over 1 trillion%. But one of the consequences of that, I'm going to show this to you, and you're going to be very surprised. Yes, it can get out of hand. And that wasn't the world record either. In Zimbabwe, this is about 10 or 12 years ago, their inflation rate was so completely out of control that they had to issue these $100 trillion bills. And that probably was enough to buy a loaf of bread. So look how many zeros there are. Ooh, that's a lot of zeros. 14 zeros, $100 trillion. This is probably equivalent to maybe $1 US. So it happens. It has happened throughout history. Imagine yourself, everybody in that country is technically a trillionaire. But what is it worth? Ooh, not much. Yeah. So you can see sometimes large numbers pop up in the real world. And this is one of those examples. Yeah. This will haunt your nightmares, I bet. $100 trillion, oh my God. And it buys a loaf of bread. How is this possible? That's right. You have nothing to worry about. US inflation is so low. It's like 2% a year. Here it was some preposterous amount of money, like 80 quadrillion% per month, I believe was the number that I saw. And that's per month. That's a lot of inflation. All right. Anyway, so let's look at some of these examples. We have, for example, all of these can be reduced. And by the way, you don't normally bother with scientific notation unless the numbers are quite large. These numbers you probably wouldn't apply it to, but you could if you needed to. And you can see the point of all of this is that whatever this number is, you want to rewrite it in such a way that there's a single digit before the decimal and the rest follows. Okay, so that's how you decide what the exponent is supposed to be. You want one digit before the decimal, the rest will follow, and whatever exponent you need to make that work is what you're going to use. Okay, so a number in the hundreds will end up being expressed as something times 10 squared. A number in the thousands will be expressed as something times 10 cubed, and a number in the 10,000s will be expressed as some number times 10 to the fourth. Okay, so it's not that difficult. I don't know if your calculator has this capability built into it. I'm going to say probably not. But if you do try to multiply, let's say, two very large numbers together, it will produce scientific notation for you. In fact, why don't we try this as an experiment? Why don't you go to your calculator and type in, oh, wait a minute. I think I see it here. There we go. Here's a fun experiment. Go to your calculator and type 1. And if you next to the 1, there's a button called EE. And then type 12 and see what happens. Oh, you need an equal sign. What happens? Look at what it did. It gives you back a trillion with all the zeros. I didn't even know that was there. So let's try one of these. I'm not sure how that would work. I don't think it's offering to turn it into scientific notation for you. I think that all it's doing is offering to turn, let's see, let me try this. I think what it's actually doing is the reverse process. It's taking scientific notation and working it backwards. So like, let's try this one. Let's just see how it reacts to this. 3.2154 double E4 equals. Yeah, see, what it's doing is a kind of the reverse of what we want. It's taking what is already scientific notation and turning it back into the original number. I don't know if it can go both ways. I'll have to investigate that. That would be kind of cool. Okay. All right. Anyway, so oh, I see the old clock is getting along there. I just want to remind you too, let's just do this and then we'll stop. What about the negative exponents? Let's review those as well. Okay, so for example, 10 to the minus 1 is 1/10. 10 to the minus 2 is 1/100th. 10 to the minus 3 is 1/1000th, all the way down here to 10 to the minus 6, which is 1/1,000,000th. Now, here's an interesting thing to note too. When you have a negative exponent, these, by the way, you might recall are called leading zeros, which means the number of zeros after the decimal point before the first number, which is not 0. The way this works with negative exponents is there's always one less leading zero than the exponent. So for example, 10 to the minus 6 has 5 leading zeros. 10 to the minus 5, if you notice, has 4 leading zeros. So this, I'm hoping, will help you remember what these numbers are supposed to look like. Okay, so let's, and all the way up. This one has 1 leading zero. And finally, this last one has no leading zeros. Okay, so sometimes you have enormously small numbers. You like, for example, if you remember from high school chemistry, the weight of an electron is some preposterously small number, and you would normally use scientific notation to represent it. All right, so I guess we don't want to get too carried away here with this. Now, don't forget, what I'd like you to do is work on those first two problem sets for Monday. And again, just you don't have to hand it in. All we're doing is reviewing it just to make sure we all understand what we've done so far. And then we'll dive back into this good stuff. And who knows, maybe I'll find some more exciting videos for you. Boy, there's a treasure house of math videos on YouTube. It's just a question of finding them. All right. So in the meantime, and it's Thursday. That's right. So you're looking forward to a weekend, aren't you? Very nice. So, all right, unless there's any last minute questions, I guess we'll knock it off right here. All right. Don't forget those videos. They were cool. And remember, the links are on the Moodle if you want to watch them again or show them off to people you want to impress with your math knowledge. That might be a possibility. Don't you find yourself kind of getting a little proud of your math knowledge here? You should. Okay. All right. So I'll see you on Monday then.
Thank you.
All right.
Take care.
Nice weekend, Professor.
Bye.